So suppose you have some sort of curve, which is, let's say, a negative cubic shape. So just draw one really briefly. Now over here, we're going to inspect a few things. Now remember how when we look at these 2 points over here, so this minimum turning point and maximum turning point. Now we call this a minimum, but is it really the lowest point on your graph? Well, not really, right? Because you can see that this one over here is actually your minimum. And is this maximum turning point really a maximum? Not really. We can see that this point up here is actually a lot higher. Now, in this case over here, this is where we need to differentiate what kind of maximum this is and what kind of minimum this is over down here. And the way we describe these is we call these ones over here, the ones in the middle, locals, or a local maximum, local minimum, and the ones that are actually the highest point or the absolute maximum, that's what we call it, and down at the bottom here, what's actually the lowest point is called the absolute minimum. So I'm just going to do a bit of labeling here. So if we have point A up here, then this is what we call an absolute maximum, just say absolute max. Over here, point B, this is a local minimum. So it's still a minimum turning point, but we call it a local because it's just the minimum for this vicinity over here. And if we were to look a bit further in this graph, you can see that this is an actual minimum, which has a point even lower than where this minimum over here is. And point C, again, this is a maximum turning point, so it is some sort of maximum, but it's not the absolute maximum. It's just the maximum around that area, so we call this a local maximum. And down here, this is definitely the lowest point on our graph here, so we call it the absolute max. Sorry, not absolute maximum, the absolute minimum. Okay. And we're going to just look at a few functions down here and see where we can locate some of these points with these characteristics. So absolute maximum, local minimum, and absolute minimum. So down over here. So suppose we had this function over here. So it's got a combination of logarithms and a polynomial over here. And it's obviously restricted between x equals to 1/3 to x equals to 3. Now we want to locate endpoints. So we're going to alternate to our CAS page over here a little bit. Now I'll just open up a new document. Okay, just cross this one out. Don't know what I was doing there. Now this over here. Okay, so first of all, whenever you approach this kind of question, just make sure you define the function as you see it. So ln x minus x squared plus 8. So I'm just going to do this real quick. Menu 1 to define f of x is equal to ln x minus x squared plus 8. And we don't worry about the domain. We'll put in the domain whenever it concerns us. Okay, so we have that defined. Now to find the endpoints, we're going to slot in the endpoints of the domain. So the domain starts at 1/3 and ends at 3. So f of 1/3. Okay, so we're going to end up with, we'll work in approximate form for this question. Actually, it says to work to 2 decimal places. So 6.79. And pressing Control Enter will give us another value to 2 decimal, or in approximate form, it's 0.0986. So this rounds to 0.10. Let's just write both these now. So for endpoints, so part A, that's what we're doing first. We're going to have f of 1/3 equal to 6.79. This is our start. And f of 3 gives us 0.10 rounded to 2 decimal places, and this gives us our end, or our endpoint to the right. And this start over here is the endpoint to the left. Okay, so course, this actually doesn't answer the question. It says endpoint over here, so just write this in coordinate form. So 1/3, comma 6.79, and the other one is 3, 0.10. These are the two endpoints. For part B over here, so write this down. Scroll back to the question. Find all stationary points to correct the two decimal places and justify their nature. Now, of course, if you want to find stationary points, what we're going to do is we're going to set f dash to 0. So first of all, we need to find what f dash is on your CAS. So if you want to do this, and we're going to reuse this function a few times. So on the way, I'm going to say that g of x, so g of x is just a placeholder for f dash, is going to be the derivative. Now to find derivative, calculus, oops, let's go back a couple steps. So calculus, and right at the top, derivative of x, derivative with respect to x of f of x. And you can see here that if you type in g of x, that we end up with 1 on x minus 2x is our derivative. Okay, we could have done that by hand, but I mean, just while we have the CAS out, just make sure that that's our function. Okay, so we want to make this equal to 0 for stationary points. Okay, and since we're running out of space, then I'm just going to write down the two x values over here, and we can do our nature test. So x is equal to what for our stationary points? Actually, how many should I be expecting? So over here, we set our derivative equal to 0, solve for x. So 3, 1 for solve. G of x is equal to 0, comma x, that's what we're trying to solve for. Press Control Enter, and that gives us two values in decimal form. So we have negative 0.707, or negative 0.71, let's just use that. I think this is approximately root 2 on 2, but let's go with what the question is requesting. And positive 0.71, rounded to 2 decimal places. This gives us the x coordinates. So obviously we need to sub these back into f of x, the original function, to find the coordinates. But before we do that, let's just find the nature of these stationary points. So to do that, let's use a different color. Use yellow. X, f dash of x, so this is a gradient, and slope. Okay. Alright, so first of all, we know that, what do we know? We know that we have a derivative of 0 when x is negative 0.71, and the derivative is also 0 when x is equal to 0.71. And the slope, of course, is flat at both these points. Let's make this a little bit flatter. Yeah. Okay. Beggars can't be choosers. Now over here, we need to see what happens on either side of the stationary point to determine the nature. So over here, we're going to find out what happens at, let's say, x equals negative 1. So any number to the left of negative 0.71, but below 0.71. I'm going to use this value over here of 0 to use, we're going to use x equals 0 to see what the gradient is on the right of negative 0.71 and on the left of 0.71. Over here we can use 1. Okay, just because this is larger than 0.71, it's still a whole number value. So let's plug these in. So on your calculator, we need to find the gradient at each of these values. So negative 1, 0, okay, that isn't too great, and 1. Okay, so I'll just write down what we know first. So we have g of negative 1, which gives us 1, and g of 1 gives us negative 1. So the slope here will be positive first, negative right at the end. Now what's happening over here? Now actually, it seems like that, well, when we first observe the function over here, that this domain over here, even if you wanted to restrict the function within this domain, naturally because of this logarithm term over here, that you actually got an asymptote at x equals 0. So there should be an asymptote there. So you can't actually use x equals to 0. And we need to use a couple of other stationary points. So just to demonstrate what this means on a graph, it may look a bit clearer. So I'm just going to draw the graph real quick. So drawing the graph of f of x. Okay. Okay, so drawing the graph sometimes actually tells a lot of stories. Now over here, remember that you can't actually have the derivative, sorry, you can't actually have a negative value inside your logarithm. So just going back over here, x can't be negative. So what we did over here, a lot of this is actually void because you can't actually have negative values of x. So always check your domain before you actually proceed. Over here, we can't use these because the domain actually says we're going from positive 1/3 to 3. Having any negative values we deem void. And also that's why I can't use 0 here. So that's my mistake. I'll just pretend that didn't happen. Okay, mistakes happen. And just learn how to deal with those. Okay. Now over here, we can't use 0, but in any case, maybe we'll try 0.5 then. It's still on the left of 0.71, but it's also within our domain as well. So going back to the calculator page, 0.5 is subbed in, get 1. So slope is going to be 1 over here. Oops. I drew the slope there. So it's a positive gradient. Now you can see over here it's a maximum. Obviously you can see from your graph page over here that you also have a maximum over here. Now you can't just say to yourself, well, I know it's a maximum, right? But if you want to justify its nature, you do have to use this nature test over here to demonstrate that the values of the gradient on either side of your stationary point behave in such a way for our stationary point to be a maximum. So this case over here, what we're going to do is we're just going to cross out this one over here. You know this is void because it's not within our domain. And we can simply say as our final solution that at the stationary point at 0.71, comma, now what's the y coordinate? This is where we need to sub back into f. So let's use a more precise value. So we're just using this value over here to more decimal places, and then we can round off. So we have 7.15. 7.15, and this is not just a maximum, but an absolute maximum. The reason for this being absolute maximum, now we can tell that this is a maximum due to our nature test over here, but it's absolute maximum because this 7.15 here is higher than our endpoint of 6.79. It's also higher than this endpoint, well, the right endpoint is at 0.10. But saying that it's absolute, you have to actually graph it out to see what this is. So for this one over here, just look at your CAS. So just underline this in green. So you need to look at your graph or whatever's on your CAS. Okay. And so the absolute part, you have to do through observation, either from your handwritten graph or from your CAS graph. Okay, so let's move down here for the next one. Now f of x is equal to x squared cos of e of x. very similar question, just quite a different function over here that we're dealing with. So first of all, let's sketch it out, and this to prevent any similar mistakes to what we did before. So it gives us a very clear idea of what the restrictions of the domain are. So over here, let's just make a new problem. So we can still use f of x, but we do have to insert a new problem. So that's document 4.1. Over here, we want to define f of x equal to x squared cos of e. Can't just type in e, got to use this button over here. And e to the x. Yep, that is it. Okay. So approaching a problem like this, you can't go straight to doing the algebra, but I mean, you know what happens when you don't sometimes. You can actually run into a bit of trouble when you're graphing it out and finding stationary points. So just treat graphing as your safety net, and it gives you a preview of what's to come. So the domain is between 1 and 2.2. So 1 and includes that, so control equals. So less than or equal to x, and less than or equal to 2.2. Okay, so we'll just get a better view of this. So just changing your window settings just a little bit. Say -5 to 5. That should be enough. Moving this across, and you can see that there should be 2 stationary points. That's what we're going to expect when we solve for the green function equal to 0. So while we're at it, actually, we'll solve it part by part. So we'll find the endpoints first. Of course, you can use the trace function here, just by pressing menu 5.1, just to get a good idea of what kind of value you should be getting. So about 1, -0.912. But we'll just double check that on the graph page. So we want to grab the endpoint at x equals to 1. Okay, so not quite. It's actually no, that's what we got. So that was our y coordinate, and then f of 2.2. So if we just press Control Enter here for the decimals, and that's what we're going to get. So let's just jot that down. So for part A, we have endpoints at 1, -0.911 and 2.2, -4.46. Okay, and now we need to know what kind of stationary points these actually are. So, actually, sorry, these aren't stationary points. Now we need to work out the stationary points first of all, and work out the nature. So over here, part B, going to let f dash of x equal to 0 for stationary points. So again, we can use some other letter. Let's say g, just for consistency, and this is going to equal to our derivative function. So 4.1 to bring out your d dx and f of x. That's what we want to derive. So when you type out g of x, you don't have to do this step. You find your derivative expression. So I'm just going to undo that because we don't actually need that. Just showing you that if you do ever need to record an expression for your derivative, you can just type in g of x after defining, of course. And over here, we want to solve for when our derivative function g of x is equal to 0. We're solving for x, so comma x. Okay, pressing enter may not be a good idea here. Let's try Control Enter. And it seems like we have multiple solutions. Of course, you're going to expect that with a trig function. And the reason why we end up with this is because we didn't define our domain, or we didn't restrict the domain. So remember that our domain is between 1 and x is between 1 and 2.2. So pressing Control Enter, this gives us two x values for the two stationary points that we were expecting. So one at 1.26932. So just while we're at it, you can actually find out the exact coordinate, because that just gives us the x coordinate. So the y coordinate for the first one, and f of 1.86378 will give us 3.42657. A lot of numbers there, but of course, just round it to two decimal places. So we have SP at two places. Okay, so 1.27ish and negative 1.47. 27, negative 1.47, and the other one was 1.86, around 3.43, rounded to two decimal places. Okay, so from over here, of course, just finding the nature of these stationary points requires us to do a nature test. So what we're going to do is draw up a table again. So x, f dash, and slope. We want to compare all of these among different values of x. So over here, let's jot down x equals to 1.27 and 1.86. We know both of these have a gradient of 0, so our tangent is going to be flat. Now after that, we can jot in some values in between. So let's say, so what's in between 1 and 1.2? We'll use 1.1 here, because that's within our domain between 1 and 2.2. Use 1.5 here. That's fine. And we'll just put down maybe just 2 over here, 2.0. Okay. So we're going to slot these into f dash. Remember, f dash by our Kaz's definition here is just g. So let's put in 1.1, put 1.5, and 2, or 2.0. Okay, so we end up with a negative gradient first, so negative 2.68. So these numbers don't have to be especially accurate, because all we're looking for is the slope here. So negative slope, 1.5 is positive, so we have 9.13. Positive slope, and negative 24.63. And this is negative. Okay, and from here you can see that you're going to have, first of all, a maximum. So just going from here to here, this is the max. Oh, sorry, minimum, because you're dipping down. So this is the minimum, and for the next set, we're going to have a, let's see, and we have a maximum over here. So this means that the first stationary point at x equals to 1.7, this one's a minimum stationary point. This one's a maximum stationary point. But depending on whether these are actually absolute or local, we need to look at the graph. So just going back over here, Control right, you can see over here that the minimum, the first minimum or the first stationary point you see, or the only minimum I should say, is a local minimum, because the endpoint here is much, much lower. You can also see that from looking at your endpoint as well. You can see that your endpoint up here goes down as low as negative 4.46, and over this minimum over here only goes down to negative 1.47. So clearly, you can see that this one over here is your absolute minimum, and this is your local minimum. For the maximum over here, Now you can see on your graph that this is quite clearly the highest point on your graph. So this one over here is an absolute maximum of a stationary point.